All right, hello everyone. So today will be our Lab10 filters. Okay, so before I talk about the tasks, there are a few things I want to let you know. So first of all, the impedance. Okay, so I mentioned this before. So impedance is kind of like a resistance to resistor, but the impedance of a capacitor is this equation, right? So it's 1 over j omega fc. The omega is equal to 2 pi. And the impedance of an inductor is j omega fil. So you can see here the impedance of a capacitor and the inductor is changing with the change of the frequency. Okay, and um, another thing I want to let you know is the voltage gain and the power gain. Okay, so in lab 8, which is the op-amp lab, you already play with the voltage gain, which is just V out over V in. So voltage divided by voltage. So that's the voltage gain. So for example, if you have a inverting amplifier, the output is 10 volt and the input is 1 volt, so the gain will be 10 over 1, so it will be 10. And sometimes we will use another unit called decibel, okay, so which is the power gain, and the unit for this is dB. Okay, so the relationship between the decibel and the voltage gain is this equation. Okay, so here are some quick conversion. So negative 3 dB is equal to 0.707 voltage gain, and the 0 dB is equal to a gain of 1. Okay, and the 3 dB is 1.41 voltage gain, and I think this one is important for today's lab, negative 3 dB. So yeah, just remember this one. This one will be important for today's lab. Okay, so then let's talk about the first task. Okay, task 1. So which you're going to build a RC low pass filter. So it's just simply a resistor in series with a capacitor. Right, so the circuit will be something like this. Okay, you have input, which you will use a function generator to generate a AC signal. So it will be connect to W1, and then you have the resistor and also capacitor in series. And here will be the ground. Okay, and then you can use channel 1 to measure the input. So 1 plus connect to W1, 1 minus connect to ground. And then you can use channel 2 to measure the output. So 2 plus channel measure the output, 2 minus connect to ground. Okay, before you actually build the circuit, you want to make sure you calculate the resistance and capacitor value. Okay, so you will use this equation. Okay, the cutoff frequency equation, and the cutoff frequency is already taught given in here. So you will just plug this value into your equation, and then you can get the RC value. And this function is get by the transfer function. Okay, so this is a transfer function for the RC low pass filter. And I'm not going to go through how to do the transfer function, but you want to make sure you check the example in the line manual. So that goes through the low pass filter transfer function of the low pass filter. And then you can use the same method to get the transfer function for the high pass filter. Okay, so let's see. Okay, so after you build the circuit, you apply a 1 volt peak-to-peak sine wave. Okay, and then in step number 4, you're going to sweep the frequency from 10 hertz to 100 kHz. Okay, so one way you can do this is you can manually change the input frequency. Okay, so which means you can use a wavegen and manually change the input frequency and record the data and make a data table. And another easier way you can do this is you can use a network. Okay, so that's function in your in the waveform of your AD2. So I will show you how to do this later. Right. So and in this step, the last sentence is require you to record at least 5 points per decade. So what that mean is each decade is 10 times difference. Okay, so for example, from 1 hertz to 10 hertz, that's 1 decade. From 100 kHz to 1 megahertz, that's also 1 decade. Okay, so that's require you. So for example, 5 points per decade, so which means you want to plot at least 5 points from 1 hertz to 10 hertz. Okay, right. So then you can plot the gain and the phase response. Okay, so if you was using the, if you are going to use the network, you can just get the plot from AD2. Right. So then the okay. So after you do the plotting, the plot will be something like this. Okay, so this is the magnitude response plot. The x-axis is the frequency, the y-axis is the magnitude. So this one is a low pass filter, which means when the frequency is low, the signal can go through. So that's why here should be the 0 dB. Okay, because 0 dB, the voltage gain is 1, which means the signal can just go through. And then when the frequency increase and when it's reaching the cutoff frequency, the signal amplitude of the signal is going to decrease. And when it starts to decrease, it's not going to decrease immediately. Okay, it has a slope. Okay, and when the amplitude decrease until 0.707 Wei in, that's negative 3 dB. So that will be your cutoff frequency. Okay. So after you get this plot, you can use cursor to measure the negative 3 dB point, which should be your cutoff frequency. And this value should be close to the given value. Okay, and then in the step number 6, you want to measure the negative 3 dB by using the oscilloscope. Okay, so which you will use waveGen to apply input, and you want to use scope to and channel 1 and channel 2 to measure the input and output. And when the output reaching the 0.707 times Wei in, so when it's reaching this amplitude, that will be your cutoff frequency. Right, so make sure you can use the network for step number 4 and number 5, but when you are doing the step number 6, you need to use the oscilloscope. Okay. So then the task 2 is you do the similar thing with task 1. Only thing you change is here you sweep the position of a capacitor and resistor. And the plot will be something like this, right? So when the frequency is low, the signal cannot pass through. When the signal is high, when the frequency is high, the signal can pass through the circuit. And by the way, here in the question 6 of task 1, how you can measure the phase shift of oscilloscope is, so for example, this is 2 signal you have on your scope. They have some phase shift. Okay, so which means you can use the cursor to measure the phase shift. So you put the cursor at one peak of the signal and put another cursor at another peak of the signal. The time difference in here, and you measure the time difference, and you use that time difference divided by the period. Okay, period is the 1 over frequency is the period. Okay, and then you times 113 because one period is 316. So one period is 316 degrees. So you times that, you will get the phase shift. So that's how you do the how you get the phase shift for step number 6. Okay, so that's all for task 1 and task 3 and task 2. Then the task 3, which you're going to build a RLC band reject filter. So which means the signal will get rejected for some range of the frequency, and the signal below and above that frequency can pass through the circuit. Okay, so for this circuit, the value already given, so you just can directly build the circuit. You need to go into measure the input and measure the output. Okay, and one thing you need to know here is you want to make sure, although it's mentioned here, is you want to sweep the frequency from 10 Hertz to 100 kHz, but actually the 100 kHz is not enough for this plot, okay? You want to make sure you sweep from 10 Hertz to at least 1 megahertz, okay? If you only sweep until 100 kHz, you're not going to see the second negative 3 dB point. So after you do the measurement, and if you do everything correctly, you should get some plot like this. Okay, so since this is a band reject filter, you see this frequency range, the signal is get rejected. Okay, so then you can do the step number 4 to number 6. Step number 4, you're going to measure the resonance frequency. Okay, so the resonance frequency is right here. Okay, so the bottom point, that will be your resonance frequency. And then step number 5 is to measure the bandwidth. Okay, so in here, you have two negative 3 dB point, right? Because you have two curves. You take the difference, that will be your bandwidth. So you got two negative 3 dB point, use F2 minus F1, you get the bandwidth. And then step number 6, the Q factor, is just simply the resonance frequency divided the bandwidth. That will be the Q factor. All right, so that's task 3. Then the task 4. Okay, so this circuit will be similar with the so this circuit is going to apply on a speaker. So some of the speaker you have should have some similar circuit as this one. All right, so and remember this circuit will be used on the final project, although it will be as extra credit. Okay, so first let's go to the questions one by one. Okay, so first one, what's the role of potentiometer in this circuit? So this is a potentiometer, and when you answer this question, you need to think about, as I mentioned, this circuit is used for the speaker, okay? It's inside the speaker. And the function of potentiometer is when you tune the little knob of the potentiometer, the output amplitude will change. So you need to kind of relate the relationship between them. Okay, then step number 2, you need to check the datasheet to get the input resistance of this LM386. So I think that's a power amplifier. And it's asking you to, do you expect to be a problem for loading? Okay, so to answer this question, you need to think about the lab 5, I think task 2 and task 3, when you have the survey equivalent circuit. And when you apply 516 ohm resistor at your output, you would see the output voltage changed. Okay, so ideal voltage should be 2.5 volt for that task, right? But when you put the 516 ohm resistor, the value decreased. That's because of the loading issue. So you want to think about that question and relate this circuit to that question and answer this question. Okay, then the step number 3, you want to compute the negative 3 dB point for the filter. Okay, so although this is the circuit for this task, but the filter is only this part. After we amp, that's the filter. Okay, so which is something looks like this, and actually this is 2 filter. Okay, the left one is something like this, the right one is something like this. Okay, so you're going to use these two circuit to calculate the transfer function and set that equation equal to 1 over square root of 2. So then you solve the equation to get the cutoff frequency. So this question is like after you get the transfer function is more about the math calculation. Okay. So yeah, that's question 3. And then the question 4, you're going to start build the circuit. Okay, so the R1 and R2 is the speaker, but since this semester you most of you work at home, so you will replace the speaker with 10 ohm resistor, and you can build the circuit and you do the same thing as task 1 and task 2, and also task 3. You measure the let's see. I think you need to construct the circuit and measure the -3 dB point in question 4 and question 5. Okay. And then the last question is asking to adjust the potentiometer and describe what it does. Okay. So as I mentioned, if you understand the question 1, you should be able to do this question. Okay, I think let's see. Yeah, I think that's all for the tasks. And lastly, let me show you how to do the network. Okay, so right now I just built a random filter, and I mean a random low pass filter. I don't know what's the value of my resistor I'm using, and I don't know what's the value of the capacitor I'm using, but I just built a random low pass filter. Okay, so how to use the network is after you open the waveform, you just click on this, the network, and you will get something like this. Okay. So in here, you can set the sweep frequency. Okay. For example, I want to start from 10 Hertz and end at, let's say, 10 kHz. Okay. And then at here, I can set how many points I want for each decade. Okay, although it's mentioned at least 5 points per decade on the lab menu, I mean the tasks, but I recommend you to use like 20 points per decade. Okay, let's start at 10 hertz. Okay. 20 points per decade. Then it's going to start to sweeping. Okay. And here you can set the input frequency, and here you can change the range of plot. Okay, so for example, all right, so as I mentioned, is the channel 2 is my output, so which means the channel 1 is the input, so I don't need channel 1 here. Okay, I can just turn off my channel 1. Let's wait a couple seconds. All right, so this is the plot I showed you. So, and since you don't have any signal at this range, so I can change this to, let's say, from 10 to -20 dB. So you see this plot is what I mentioned in here. So this is similar with this one. And after you get the plot, you can click on here to measure the -3 dB point. So for example, all right, so let's say here. So that's the -3 dB point, which I can prove my cutoff frequency for the circuit I having is 1.58 kHz. Okay, so that's the cutoff frequency I have right now. And here is the phase shift. Okay, so that's how you use the network. And remember, you will use this for question 4 and question 5. But when you're doing the question 6 in task 1, you will need to go back to the wavegen and the set wavegen and scoop. Okay, so you generate a, so for example, right now I know my cutoff frequency is around this frequency. So I will generate a 1.5K hertz signal, and I can measure those plot. And let's see, I can measure the amplitude for both plot. So when, remember, as I mentioned, when the signal is at cutoff frequency, the output should be equal to 0.707 input. Okay, so my output, my input is about 1 volt. So I need to adjust my input frequency, okay, to get this value to close to 0.707. Okay, so right now, this frequency is very close to the 0.707 times input. Okay, so I can maybe increase a little bit. You see here, that should be close enough. And to measure the cursor, so you want to measure the two peak of the signal and use the, so this is delta x, so you will use this number and using the equation I showed you here to get the phase shift. Okay, I think that's all you need to know for this lab. Just let me know if you have any questions.